Hello, I'm Ryang Son from Postech. I will present my approach for the MLC school competition. So, our first thought upon reading the problem statement was, isn't it a well-researched problem? And we initially looked into how production-grade optimizers approach this. They usually employ rule-based methods like fuse cheap element-wise operations after matrix multiplication. And these rule-based methods were quite well in practice. And operator's performance is related to its definition, and we can get a reasonable estimate for performance by just identifying the operators. However, the operators in this challenge can have arbitrary cost, and fusion opportunities are unlimited. I mean, almost. So, our overall strategy was to go for search-based method. So the problem solver needs to determine the operators to fuse, retention of outputs, iteration order, and tile size. As for iteration order, link ordering is simply optimal due to the caching constraints. For other variables, it's not this simple. One observation we made is that retained tensor's lifetime is limited and fusion constraints are relaxed. So our strategy was to treat retention as global optimization, fusion as local optimization, and do global then go local later. And for the fusion strategy, we wanted to make use of recomputation, but this comes with larger search space. We searched for prior works and determined Quarch is a good fit. Quarch enumerates subgraphs first, then benchmarked them to determine each subgraph's latency. The problem of choosing which subgraphs to execute is formulated as BLP, binary linear programming. Then, the BLP problem instance is solved by an off-the-shelf solver. Using Quarch, we could consider wide range of fusion and recomputation opportunities while being able to tune the search space by adjusting convex subgraphs maximum size and BLP solver's running time. For retention, we realized that we can see this as a problem of partitioning the fused subgraphs into multiple producer-consumer chains. Our partitioning algorithm is inspired by graph connecting algorithm presented in Welder. The algorithm selects which memory to place the tensors by iterating over each internal tensor. Instead of the greedy algorithm of graph connecting, we introduce beam search to get better results. And that's a wrap. Thank you for your attention, and questions are welcome. Please post an issue in our GitHub repository. Thank you and enjoy your conference.